Hello, math gents and ladies. This is a small little section about a new tool that's at your disposal that comes from some of the ones we've already talked about. So obviously when we look at these wonderful identities that we've developed in the sum and difference identities, we can also come up with new ones as well. We're always building our toolbox. So developing a new identity, this is called double angle identities. And it's important to know, well, what's that referring to? So it says, first off, determine if you have the sine of 2a right here, is that equivalent to 2 sine a? So in other words, does that 2 just kind of come out there? Is that a true statement? Does that work? And let's determine whether that actually works. So if we look at the, again, if we look at the left side of this, the left side says we've got sine of 2 times pi over 6. If a is pi over 6, that's 2 times pi over 6, which is equal to the sine of pi over 3, which we know to be equal to root 3 over 2. Well, is that equivalent to 2 times the sine of pi over 6? Well, let's try it. The sine of pi over 6 is 1/2. 2 times 1/2 is 1. Clearly, left side does not equal right side, so that means that we can say it's false. It's not true. So how do we develop an identity? What is the sine of 2a, the sine of a double angle? What is that equal to? And how can we find that? Well, if you consider what we know that the sine of 2a could also be considered simply as one apple plus another apple, the sine of a plus a. If I use my sum identity, and instead of having a plus b, we have a plus a, go to the sine sum identity, and we have sine a cos a plus sine a cos a. And that is equal to, excuse me, and that is equal to 2 of the sine a cos a things. And we've also accomplished part 2. We have proven that sine 2a is equal to 2 sine a, 2 sine a cos a. When we look at now cosine 2a, we can follow that same strategy. Well, the cosine of 2a could be considered, well, one apple plus one apple is still going to be 2 apples. So if I use the cosine sum identity, that would mean I would have cos a minus sine a sine a. Or in other words, that's equivalent to cos a squared minus sine a squared. And therefore, we've just created a new identity that if we see cosine 2a, that is equivalent to cos a squared minus sine squared. If we look at the tangent identity, once again, we could use the tangent sum identity, and we know that the tangent of 2a could be considered as tangent a plus a, which then we go back to our tangent law and use the tangent sum identity. So clearly if you use the tangent sum identity, and now instead of a plus b you have a plus a, you end up with this expression, and if we simplify it, we have 2 tangent a's on top, and we are left with 1 minus tangent squared on the bottom. So we've created a third new identity using the identities we had from the previous day. It's important to note that just like any Pythagorean identity, it can be expressed in other forms. The identity for cosine 2a can be expressed in 2 other forms, right? Using the Pythagorean identity sine a squared plus cos squared. Okay, so notice that here's our total toolbox. This is what we've added for double angle identities, and this is the end of the line on your formula sheet. We've now got all the tools that we're going to have with trig. Okay, And so there's all the rules we have. So now we've got new identities to use, and we have to use all those things. So in example 1, use the tools that you have to try and come up with a proof for this. Don't forget, the first thing we start is by not assuming it to be true. So start with your T, and on the left side, work it together. So you can pause right now and give it a go and see if we come up with the same answer. So as you can see, what I decided to do was I looked through my list of tools, and I saw that sine 2x can be expressed as this. And I looked at 1 plus tangent squared, and I saw that I could do that. And now I'm at a bit of a standstill. It doesn't look like I can do much more to the right side. So I look at this side and I say, well, this technically is 2 sine x over cos x, all divided by 1 over, excuse me, 1 over cosine x squared. And by using the rules of rational expressions, 2 sine x over cos x times cosine x squared all over 1, we can see that the squared cancels with that, and we have 2 sine x equal to 2 sine x cos x equals 2 sine x cos x. Therefore, left side equals right side. Proven. We have proved that identity. All right. Now we go to example 2. And again, we're using these new tools to see what we can come up with. So use the identity sine 2a equals 2 sine a cos a with a replaced with 3x to determine a double angle identity for sine 6x. So what it's really saying is we can use that identity in unique ways, that instead of seeing 2a, we might see 2 times 3x, where that a value could be a multiple. So if you had this double angle identity, when you rewrite the identity of sine 2a is equal to 2 sine a cos a, we could rewrite this as 2 sine 3x cosine 3x. And so now you've used that identity in a unique way. So how could we write cosine 10a as a double angle? Again, if it needs to be a double angle, what they're really saying is, how can you write that as a double? Well, if it was a double, I guess we'd have to assume it to be 2 times 2 times something if you want it as a double angle. So what would it be 2 times? Well, it'd be cosine 2 times 5a. And so that's still going to be 10a. And then obviously we would rewrite that as, so if you rewrite that like we said, using that 2 times 5a, we end up with an identity as that. Okay. How can you rewrite tangent as a double angle situation, considering there's your tangent double angle tool? Well, the only way we can think of that in a double situation is to say, okay, well, tangent needs to be expressed in a double situation. Double what? What is still going to be equivalent? Well, it would have to be tangent 2 times what? I guess that would have to be tangent of 2 times 1/2 x. And that way we would still have, whoopsie, don't want an equal sign there. So this would be tangent of 2 times 1/2 x. That's still going to be equal to x. And now we can use our tangent double angle identity. So as you can see, using the tangent double angle identity, that's the expression that we would get for tangent x. Example 3, last one, and a common one for diploma exams. They want you to work backwards and come back to what was this in terms of a single trigonometric function. So if you see 2 sine 4x 4x, look at the patterns on your formula sheet and see which double angle identity that came from. Where does that come from? To me, that one looks like it's coming from the double angle sine identity. It looks like it's coming from sine 2 something, and in this case it must be 2 times 4x, which in simplest form is the sine of 8x. That's what they're looking for. When you look at cos squared minus sine squared, where is that? That comes from this cosine 2a identity. Well, in this case, what's the a value? Well, it must be cosine of 2. A is actually 1/2 a. So this must actually be equal to the cosine of a. A complicated way of writing cosine of a. Weird. The last one, this is sine x cos x. It looks to me like this expression is coming from that sine 2a identity, except for one problem. This doesn't have a 2 right out front here. Doesn't have a 2. Now the only way it could not have a 2 is if it is only 1/2 of that sine 2a identity. So what does it actually look like? It's 1/2 of the sine of 2a, and in this case a is 5/2. Whoopsie. A is 2 times the sine of 5/2 x, which ends up being 1/2 of the sine of 5x. And now you have your assignment.